So first we're going to take a look at the USB-IF, the organization that manages the USB protocol. We'll discuss why it's important to ensure devices pass compliance. We will then look at what the requirements are and explain how Teledyne LeCroy plays a role in this process. Finally, we'll look at an example test result from a USB flash drive that I have with me. So the USB-IF was formed by a group of companies that originally developed the USB spec. They work to facilitate the development of USB products and to ensure that they all maintain a certain standard. As of recently, there were 737 member companies, and the annual membership fees were $4,000 US. There are numerous benefits to joining the USB-IF. You become eligible to participate in quarterly compliance workshops, which I'll discuss later. You also get a vendor ID, your company listing and inclusion in the USB.org products list, and you have the opportunity to stay up to date on marketing programs, events, and any news relating to USB. So the USB logo, which is trademark protected, is designed to be used to identify products that properly meet the specification. Any vendors that wish to display this logo on their device must pass the official USB-IF compliance program. So there are two ways to achieve this certification. The first involves attending one of the 4 quarterly compliance workshops. For example, next week I'll be attending workshop number 93 in Taiwan. There's also typically a workshop in Hawaii, and the other 2 are both in Portland, Oregon. The advantage of attending these workshops is that they are free for USB-IF members. You get the opportunity to communicate with the test spec writers, and you get a close look at the compliance process. The downside is that you may be interested in achieving compliance more urgently, or you may prefer not to attend an event in such close proximity to competitors. Option number 2 is to work with an independent test house. For a fee, they'll take your product through the compliance process for you. The downside is that there can be less transparency, and if they find a problem, you may have to pay a second fee to have your device retested. As such, performing testing in-house can save you time and money. With the right test equipment, you can attend a workshop completely prepared, knowing that your device will pass all of the same tests that you have already performed with our equipment. So there are a few different stages that you must pass to achieve this compliance. You need to test electricals, which can be performed with LeCroy oscilloscopes and PERT products. I'll go through those briefly in a moment. You must also test interoperability, backwards compatibility, and Chapter 9, device framework tests, which can be performed with the free USB CV tool. However, our protocol analyzers can still be very helpful here if you wish to take a look at the traffic that was going back and forth during these tests. Finally, the focus of this talk is on USB 3.0 link layer testing. Our hardware will perform the Chapter 6 and 7 tests in official capacity for the USB-IF, so our products are the same as you'll find at workshops and test houses. So we'll take a brief look at some of the electrical test requirements. Well, this occurs with the sister division of Teledyne LeCroy with our oscilloscope and PERT products. I won't be elaborating on it too much. However, it's a good idea to show you a brief overview, so I included a few slides here. Transmitter testing is performed with an oscilloscope, and it ensures the device sends signals of sufficient quality. There are a few tests including eye diagrams, characterization of the spread spectrum clock, jitter testing. There's a wide range of tests. Here's a little explanation of some jitter testing. And a slide on transmission equalization. For USB 3.0, continuous time linear equalization is used. So we provide some tools to simplify the process, including our oscilloscopes, our Qualify tool, and our PERT products. I'll explain those a little bit more later. Here's a slide on receiver testing, which you'd use our PERT hardware to test. And just a slide on some fundamentals. Basically, receiver testing ensures that the receiving device can interoperate with compliant transmitters. So there are two stages: calibration and loopback testing. There's stage 1 and stage 2. So link equalization standards require that the transmitter equalization settings be negotiated between the transmitter and receiver. And there are a few fundamental parts to this type of testing. And again, our PERT product is very helpful for this type of stuff. But that's a different group. If you guys have any questions on our PERT products or oscilloscopes, I can definitely point you in the right places. So our Qualify is software we provide to be used in conjunction with an oscilloscope for electrical compliance. It can be used to cover a variety of different standards, including USB 2.0 and 3.0. And here's an example of a test report from the PERT software for PCI Express. And so now we're moving on to link layer requirements, which is the focus of this talk, and that's what our protocol analyzers specialize in. Because the link layer is so fundamental to the reliable operation of the link, it should be a high priority for testing. If there are problems at the link layer, many of the benefits of super speed traffic are not possible. Without reliable delivery of header packets, link performance drops. Without reliable power management, battery life suffers. And of course, it's a necessary step to get logo certification. So a few of the items tested are link and packet robustness, CRC air handling, timer deadlines, management of low power states, and a variety of others. Here's a quick picture of the USB 3.0 LT SSM. The diagram represents all of the logical states that a super speed device might enter in normal operation. There are specific rules for entry and exit for each of the states, and it all is tested. So if we take a quick walk through the link initialization, both sides of the link wake up. If receiver termination is detected from the far end, the device is moved to a polling state, which has several substates. After an initial LFPS handshake, the two sides go directly to sending the receiver equalization. This is where the receiver is supposed to perform the 5 gig signal lock. So there's a predefined pattern sent that's 65,000 symbols in length, and receivers are supposed to calibrate their transmitter. If they acknowledge receipt, it moves on. Otherwise, and they move to polling active, where the two sides are supposed to receive at least 8 TS1 followed by 16 TS2. And if the receiver doesn't see 8, the devices would cycle between RX detect and polling active. And there are several configuration fields also extracted from the TS2 sequence, followed by idle symbol handshake, and then the link is in U0. So I'll go through a few example tests that help illustrate the link layer protocol. In all of these examples, we'll refer to the port under test as the PUT. The Voyagers referred to the LVS, or the link verification system. So in all tests, a sequence of events are transmitted by the Voyager, and the response is recorded and analyzed. So here's an example of a link bring-up test, which is 7.01. To pass, the PUT must complete the link bring-up successfully. Here we're looking at a trace from the LeCroy software that was generated from our compliance suite. It shows each of the link polling substates, each event on a separate line there, starting with LFPS polling, handshake, which is an 8 to 12 microsecond bursts. It needs to be detected by each side, and is followed by an RxEQ pattern. There the devices perform equalization. Then you go to polling active, where each side sends 8 TS1s followed by 16 TS2. There are a few configuration messages there, like I mentioned. So now if devices fail to complete link training, this is where it would occur. You'd find out in this test. One side probably won't move to TS2, or the device definitely won't reach U0. It'll repeatedly try to retrain, but usually you'll be able to identify that here. So here's the second part of the test. After completing link training and entering U0, the partners must send the correct header and credit advertisement. You'll always see an LGood 7 when it first enters U0. That's just part of the spec design. So the devices should issue the 4 flow control credits, LCRED A, B, C, and D. And then the link partners perform the correct LMP exchange, which is again tested later in 7.17, which I'll come back to. There's a few of the things I was talking about. And we check that the link stays in U0 for 50 milliseconds. Test 7.03 created a lot of problems for device vendors because the test spec was actually changed when USB released the June 2010 errata. In the original spec, devices were supposed to accept link commands even when one of the CRC5 are invalid. It was supposed to make the link more tolerant to marginal link conditions. However, in June 2010, they changed the USB 3.0 spec. Now both CRC5 must be valid and identical, or the link command will be rejected. In this example, the LVS sends an LCRED A and LCRED B with a bad CRC5. The device should go into recovery after 5 milliseconds, but you can see here that the link stays up for over 1 second. The test is based on the new spec, but the product being tested here was failing. So this test specifically verified a 3 microsecond timeout. The tester waits for an LMP from the device, and then instead of sending LGood, we delay the LGood and send it right before the timeout. We make sure that the device can handle this. Test case 7.08 actually tests this rule. In this test, the Voyager intentionally inserts a CRC error in the header portion of the LMP packet. Because header packet errors are retried at the link layer, the retry is initiated. The LVS sends LMP. The PUT responds with an LBAD, indicating that it did not receive this header packet correctly. The Voyager sends the retry command and then retransmits the packet. The LGood must be resent, and the LGood must match the H sequence number, header sequence number of the original packet. In this case, the H sequence should be 0. If the device resent the packet and incremented the H sequence, let's say it became 1, the link partner would ignore it. So this mechanism ensures that no header packets are missed. So here's a screenshot of our compliance suite. I'll take a moment to show you that. But first, let's look at the 7.17 test spec. The flash drive I'm holding in my hand right now has trouble with this test. So when I'm debugging a test, the first thing I like to do is look at the spec. For this test, 717 checks that the port behaves correctly when its link partner doesn't send proper LMP packets. So we can see that the test begins bringing the device to U0, which is step 1 of the test, the link initialization sequence. Then for part 1 of the test, the LVS does not transmit either the port capability or port configuration LMPs. For part 2 of the test right here, the LVS transmits the port capability but not the port configuration, and vice versa for part 3. In each case, as you can see in step 8 here, the port under test is supposed to go to ESS disabled within the T-port configuration deadline. You can find this deadline in the USB 3.0 spec, but it's 20 microseconds to 30 microseconds. So I'll show you that in a real-world example. I won't make you all sit here while the test runs, so pretend this is like a cooking show and I have some fresh results in the oven. So here's an example of the final results from the Chapter 7 device link layer tests. As you can see, we add the test over here on the left side. You click Run up here. You also have the option to repeat any of the test cases X number of times if you want to stress test your device. So as you can see, we have an error message for test 717 indicating that the PUT did not transition to ESS disabled before the T-port configuration timer expired. We can double-click the fail message right here to take a look at the traces. We also provide an individual log for each trace, which will show you more details. Part 1 you can see passed. You can access the trace file there. Part 2 also passed. And part 3 failed, and the error message is right there. The port does not transition to ESS disabled after T-port configuration expires. So I have that open in our protocol suite right here. One thing you can do to help determine why a test is failing is to look at a passing example. So first I open 717 part 1 right here. And we can take a look. We provide some convenient markers in the trace. If you mouse over right here, you can see that the T-port configuration timer started at this point. And then right here, you can see that when the device entered ESS disabled, it was after 20.022 microseconds within that T-port configuration range. So this might not be the most visually appealing example because when a device enters ESS disabled, in superspeed traffic, we just see electrical idle. But you can also do the calculation yourself by right-clicking on this packet here, setting the quick timing marker, and then right-clicking at this point, set the end quick timing marker, and you can see the delta time was 20.022 microseconds. So there's a good example. As you can see, we never sent any of the LMPs, but the device responded with the report capability, saw we never sent anything, and went to ESS disabled. Here's an example of the failing trace. This is part 3. As you can see, we send the LMP port capability, or the device sends it. We send the port config, and they respond. But this is the test where we don't send the port capability. We start the timing right up here when it enters U0, and as you can see through all this traffic, I'll compress it, but quite a while later, it never enters ESS disabled. If you'd like to measure that yourself, you can set the quick timing marker right here. As you can see, there are 80,000 packets here. If we unstack them and scroll all the way to the bottom, we'll hide these skip sequences. You can see that almost 60 milliseconds later, the device still hasn't entered ESS disabled. So that's kind of a convenient way to measure the timings yourself. So for USB 3.1, the spec writers are expanding upon the spec. They've already added a TD 6.6, 6.7, and 3 7.1 subtests, which you can actually see we have already integrated into our compliance suite right here. They weren't able to run on this device as it was a 3.0 device, but we're working very closely with the USB-IF to implement these tests as quickly as possible. There are more tests to come. In our discussions, we've heard that a TD 7.39 and 7.40 are on the way, but none of this has been officially implemented yet. I know the USB-IF would like to start running some preliminary tests by the end of the year. So in early 2015, you can look forward to seeing the new 3.1 test spec. Here's a quick overview of our lineup. From the electrical test spec, which you can test with our oscilloscopes, to receiver testing, which you can test with our PERT system, to even cables and connectors, which can be tested with some of our other products. So here's some contact information for us. You can always email psgsupport@teledynelecroy.com. Any of our support engineers will see those questions, and we'll do our best to get back to you as quickly as possible. I know that was brief, but if you guys have any questions, I'm happy to answer anything. I'll try to get to any questions I can, and if not, I'll make sure to send you an email response. So let me see.